Color is one of the most ubiquitous expressions of chemistry in our everyday lives. When we look at a chemical compound, or when we look at anything and we see color, why do we see it? What's going on there? What chemical information can we get from it? So what we've got here are 4 different food dye samples. Each one's a different color. Now what I want you to do is take a moment, think back to what you've been told in the past. What gives rise to this color? Why does it appear to be the color that it is? What most of us learn is that something that looks green is green because green light is bouncing off of it. Something that looks red is because red light's bouncing off of it. And this gives us this kind of appearance information, the way that it looks to us. But how do we deal with something like a set of different green colors? These are all green-ish. How do we make sense of what gives rise to these different colors? They all look pretty much the same. Are they the same? What kind of information can we get about this chemically? And the reason that this is more tricky than this simple explanation you have gotten in the past of it's blue because blue light's bouncing off of it is because why blue light bounces off of it, or whether blue light is actually bouncing off of it. What chemical compound, what chemical interaction, what's interacting with the light to make it so that this appears blue? Now, the human mind doesn't do a fantastic job of splitting this information up. So we're going to use technology. What we have here is a nice little tabletop spectrometer. Inside of this, there's going to be a light source and a little prism, essentially, that's going to rotate, and it's going to make it so we shine light through a sample. And then we're going to use, there's a camera over here, and that's going to detect what light's making it through, and we're going to see that show up on the screen over here. So we can go ahead and start investigating these different chemical compounds. So we can take our red sample, and we can, instead of just using our eyes and saying, oh, red light must be bouncing off of this sample and that's why it looks red, we can go ahead and have the spectrometer in the computer analyze it for us, and we can see what wavelengths of light are actually being absorbed and what wavelengths of light are actually being transmitted by the sample. So we can go ahead and just hit go. Let's erase and continue. And here we go. Boom. This is our red sample. And what we can see here in this absorption spectrum is we can see there's actually no absorbance in the red region. So there's no red light being absorbed by this sample. But we've got a significant amount of absorbance here in the greenish blue area, and we've got a maximum peak right here, right at the edge between green and blue. So this red sample, not only is it not interacting with the red light, it's significantly interacting with the green light. And not surprisingly, green is the complementary color to red. Let's go ahead and look at this for another sample and see if the same thing kind of keeps happening. Blue. Go ahead, take a moment, think to yourself, what's the complementary color of blue? Is this going to be bouncing blue light off of it? Is it going to be absorbing blue light? Why can you look through this sample and you can see kind of a blue tint through it? So it's not that all the blue light's getting bounced. What's going on there? We can go ahead. Again, using our spectrometer, we can analyze the chemical compound and get at the information not in terms of how our mind is interpreting, our eyes interacting with the wavelengths and our brains interpreting that color. We can actually just focus in on the light interacting with the chemical compound. I'm going to go store that latest one. Ta-da! There we go. In this situation, you notice nothing is being absorbed over here in the blue area. We've got this little funny tick off in the purple that has to do with the quality of the spectrometer. But over here, where we see the tallest part of the peak, what we call our lambda max, our maximum wavelength, is over here in the orange range. So that lambda max being in the orange is going to give us information about how this material is interacting with light. Make that bigger. There we go. Yes. Now we can also take this idea. I'll do one more. Yellow. Yellow. Wow. Yellow absorbs over here in the purple region, which makes sense because the complementary color of yellow is purple. Now what we can do is we can start to think about, well, what happens when I take my colors and I start mixing them? I didn't do green yet. And I didn't want to do green yet because I wanted to do a kind of thought experiment first, which is to say, let's see here, how do we think about purple? There's a couple different ways we can think about purple. One of the obvious kind of elementary school ways that we can think about purple, that's kind of a weird purple too, is we can mix blue and red. So I'm going to take blue, put in some blue food dye, I'll put in red, swirl it around. You see, I've got some, well, it doesn't show up well on the camera, but I've got essentially two different kinds of purple. They really look kind of gray on screen. So now what we're going to do is we're going to analyze these two. We've got one that's kind of a mystery purple, and one that I made right in front of you that's just a mix of blue and red. So take a moment while I get this set up and think to yourselves, what should a mix of blue and red look like? Is this just reflecting purple light like we learned about in the past? Is there going to be something else going on? Going back to the spectrometer, so this is our purple solution. Going back to the spectrometer, we'll store that latest run. Ah, what do you notice? What do you see? This line, this golden colored line, is this purple mix. That's a mix of blue, which absorbs in the orange region, and red, which absorbs in the bluish-green region. So we can actually have, in these cases where we have mixes of chemicals, we can have these situations where we have more than one peak absorbing. And we get one peak for each chemical compound inside of the sample. We can now go back to this other mystery purple and we can say, hey, is this mystery purple something that is just purple, or is it also a mix of blue and red? Mystery purple's turn. And I don't know the answer to this one yet. Ah, okay. So here's what we see for mystery purple. Mystery purple lines up really well with the red peak over here, the red-looking compound which absorbs in green, and it lines up really well with the blue-looking compound which absorbs in orange. You'll notice, though, that the peak heights are different. It turns out, through a different kind of experimental equation, we can relate that peak height to concentration of each compound in solution. That relationship between peak height and the concentration of each compound in solution is Beer's law, which will be in a different video. Okay, now I want to go ahead and see, is every time we have a mix of colors, green is made from blue and yellow, of course, are each of these blue and yellow? In order to test that, we're going to test three different things. I've got this green, we've got another green that I made. This one's made out of blue and yellow. This one was a mystery green solution. And then this is a different mystery green solution. What's going to happen in each of these cases? Notice here, while they all look green, the important thing with spectroscopy is we can actually use the spectrometer to get at chemical information, to tell the difference between these different compounds. So here's our first green solution. Okay, so this green solution, you notice it lines up with the blue looking solution that absorbs in orange, and it lines up with the yellow looking solution that absorbs in purple. So this green is actually created from a mix of blue and yellow. I've got one more solution that I'm going to do. I'm getting a little antsy for the exciting one. So here's one of our other green solutions. And the question is, are we going to get the same thing? Are we going to get a yellow-looking peak that absorbs in purple and a blue-looking peak that absorbs in orange, or are we going to get something else? Whoa, too much concentration. So this one is actually quite a bit different. So it's absorbing past what this thing can detect. So it's got some other things going on. That's going to ruin it if I take it out. We'll put it back in. So this one is absorbing off in the purple, but it's also absorbing all the way over here through all of the red. Not necessarily peaked at orange, but through all of the red. So we can tell by looking at this absorption spectrum that this chemical is some different chemical from the other things that we were looking at. Even though all of these greens look the same, they're not the same. There's some difference. This last one is actually a nickel solution. So the reason that it's green, these green solutions are green because they have blue food dye and yellow food dye mixed into them. This one is a nickel solution, which absorbs mostly in the red region. And we know that the complementary color to green is red. So that way, we can see that this kind of has some relation. This absorbing in red is really what makes the last solution look green. Now, the way that we distinguish, well, let's see if I can line that up real quick. Seasick. The way that we distinguish different chemical compounds having a difference in the way that they absorb or in a difference in how they absorb is this special Greek letter epsilon. Hopefully you can see that. That is to say the molar absorptivity. Every chemical compound has a molar absorptivity associated with it. That is to say we've got some relation of the chemical's behavior to how it absorbs light. And what we can see is not only does it change for each chemical compound we're looking at, but it's also going to change as the wavelength changes. We have peaks and we have valleys. As the wavelength changes, we also see a difference in absorbance. So that epsilon, this molar absorptivity idea that we're going to talk about more in the next video, is really going to depend on the wavelength and on the chemical identity of what we're looking at. So hopefully this changes the way you think about color a little bit. Instead of it just being a straight, oh, it's bouncing, it's reflecting light, it could also be absorbing light. And it could be something looks green because it's blue and yellow, or it could be green because it's absorbing red. Our simple answer that we've gotten in the past is oversimplified for what's actually happening and how we can get at chemical information for the different compounds.